Thanks for inviting me. Thanks for this opportunity, and thanks for all of you to be here and willing to listen to our work. I guess sound and such should be okay. I'm going to get louder as we go, so no worries. Yes, without much detail, I'm going to discuss about a recent experiment that the Google AI team did in collaboration with our colleagues and friends at Stanford, Princeton, and Max Planck. I'm also highlighting a couple of the members of the Google team who were more directly involved in this work. So I have limited time, so let's just get to the our narrative on our version of the story. We are all very fascinated by crystals, and I think the reason is not that you can use crystals for fortune telling or something. It's mainly because you have a system of many degrees of freedom, many interacting particles, and yet they choose to pick a order state when you cool it down, or when in their ground state, they form a periodic pattern in a space. And it's not very hard to find examples of it. You have liquid crystals, you have regular crystals, spatial crystals, you have ferromagnetism. Finding many interacting particles forming a periodic pattern in a space is not very hard. So you start thinking maybe, you think about Lorentz invariance, and time is a space and space is time, although it comes with a negative sign in the general, special relativity. You might say, well, maybe I can look for systems of many degrees of freedom that form periodic pattern in time. And as you start thinking about that, you realize it's not as simple. You think about a couple of examples, a clock, child in a swing, periodic parametric amplification, solar systems, a couple of examples, but you realize that what is common between these examples is that they only have very few degrees of freedom. And you think harder and harder to come up with examples that you have many degrees of freedom, and yet they show periodic pattern in time, and you realize actually it's very hard and you cannot think of many. And hence, that's how we define time crystals. Can we find a system that oscillates indefinitely and is made of many degrees of freedom in an isolation without energy input or entropy dissipation? And the answer is, well, it's not easy. So that's interesting. That's the challenge, and that's what we are here. Essentially, what we are saying is that if you have a crystal, if you perturb it, you change the temperature, you introduce local perturbation, and if you watch it for a while, it's going to just go back to where it started. But if you start with lots of degrees of freedom, like a bunch of pendulums that are showing some nice periodic pattern, if you come back and look at it, most likely it's in some disordered state. or if you manage to get to see it go forever, it's probably because you're driving it and it dissipates entropy somewhere else, so you're stabilizing by using these closeness that I'm highlighting as a part of the definition. So, but is that really impossible? Well, I think it's challenging, and there is also something impossible about it. What's challenging about it? Well, if you're asking to have a system which oscillates between two states, two configurations or several configurations, and it repeats this pattern. So second law of thermodynamics doesn't make it impossible, but makes it very challenging. Essentially, well, the second law says entropy of a closed system of many degrees of freedom is just going to increase, or it's going to stay constant. It doesn't say, it says it is not going to decrease, but it doesn't necessitate that it has to increase. So keep it in constant is just a very hard experimental challenge. So essentially, as time goes by, the entropy of the system is going to increase. But there's also something totally impossible about it too, which makes it harder. And that is was tried to be is figured out from the work of that started by Frank Wilczek. Well, we're looking for perpetual or indefinite motion, right? So we say, well, as physicists, we are very familiar with it. You cool down a ring, superconducting ring, and you introduce a little magnetic field, and it's going to go show up persistent current forever. So it's not hard. We're familiar with that. But the issue is that doesn't bring time invariance. You look at it one day and you come and look at it 10 days later. There's no way to distinguish instance of time with that. So it respects time invariance. Well, Frank Wilczek suggested that, well, if we introduce interaction between Cooper pairs, and they can form lumps, and these lumps can oscillate in this ring, and then you can really tag instance of time. Instance of time become distinguishable from each other, and you get oscillatory current in the ground state of this system. And then it took some discussions, particularly the work of Watanabe and Oshikawa 2 years later showed that, well, they first say, okay, let's define what we mean by oscillatory behavior. And they say, can we define a two-point correlation between two distinct points in time and in space? And can we expect to show a non-trivial two-point correlation pattern? And after careful analysis, they realized that this is impossible, and this is bounded by 1 over the dimension of the system size. So you take the system larger, this has to be flat constant. So realizing this at least two-point correlation function, they prove is impossible. So in the spectrum language that it comes handy for our discussions, we are saying, look, if there is an energy spectrum, this ground state and these are highest state, hoping that to see some oscillation or some order state which shows this oscillation in the ground state is impossible. So you're not going to see that in equilibrium. So we have to go and look away from equilibrium. You know, being careful or being cautious, we just take the minimum number of steps away from equilibrium. We just get to their closest cousin. That's derivative system, or you guys call it Floquet system. And a priori, there is no good reason to think that's any advantageous. You know, you get the spectrum now wrapped up on a unit circle, so these points or these would be your energy eigenvalues. Now they're a phase of a unitary. But it's not going to give you time crystal for just by just doing periodic driving. In particular, is a very bad choice because it's commonly known that you have a driven system is just going to absorb energy from its drive and it's just going to heat up and is going to be in some highly entropic states and which defies any ordering. However, there was this clever or discovery or finding that came really important for this matter, and that is the presence of many-body localization. So you have strong interaction in the system, strong disorder in the interacting system, then there is a chance that localization put a cap on energy absorption and the system does not heat up to infinity. So in other words, this physics of many-body localization is telling us that there is some hope that if we could realize a many-body localized phase in this periodic, under this periodic Hamiltonian, then there is a cap on the entropy that the system gets into, and there is a chance that we can stabilize a phase.
I don't want to like start fight, but I think at some point in the slide there is a change of notion from equilibrium to long transient. Because I would argue, and we don't need to discuss it now, if you have Floquet drive, so it's like you couple to the cavity, the only equilibrium is infinite temperature. There is no other equilibrium. It maximizes entropy and so on. But then what you're saying, there could be infinitely long steady state. But infinitely long steady state can be even in, say, MBL if it exists, even without driving. Whether it oscillates or not, it's a different question, but it doesn't violate any of, I don't know, Oshikawa's theorem and so on. So we are kind of, I just want to be clear, I think. So we are switching here from equilibrium to infinitely long transient state. It's important. And this can be done with or without driving.
Okay, well, I'm going to get to it maybe that it's really come on what do you expect from MBL and property of MBL. The whole DTC discussion is really a study of what you believe MBL system can do and cannot do. So maybe just focus on what our experiment tells us about it. And also, by the way, this period doubling comes that over the systems that we are considering, the eigenstates comes in pairing, and there is nothing sacred about period doubling, and by no means it means the time crystal. It's not anything new about period doubling. So that's rather a side product of the physics. Okay, let me introduce the pulse sequence that we use. Is starting from the transverse ising model. We apply the kicked version of it. Essentially, we get okay, some of your color pins are not working. You get you apply a layer of single qubit rotations. This is like a Rabi drive with amplitude with angle g. When g equals to 1 is exactly pi drive. It follows by a layer of entangling gate. This is a C phase gate. When phi's are pi, this becomes a famous CZ gate, and followed by a level of by layer of local fields to individual qubits, which is we use to introduce this order. And this is the in the exponential form, the Hamiltonian, if you are more familiar with. But I want to make something very clear as this discussion of MBL popped up even before I was waiting for it. So let's think about the uniform coupling limit. This is a very important distinction. Let's just imagine for a second that these couplings were uniform. What happens is that you have a bunch of qubits, you rotate them, and they see this disorder landscape. And then you rotate them and G is equal to 1, so you're exactly flipping completely. And they see the same disorder, but now it's flipped, is as if they have seen the opposite of disorder. So in 2 cycles, you see this landscape, the way it appears to the qubits is exactly canceling each other. So when this disorder is uniform in the entangling gate, there's a very little chance that you can realize many-body localization. So it was a key thing that the disorder in the entangling gate has to be non-uniform. In fact, this physics has been known for many years. As John Lennon was talking about it, is slightly different context, but you know, kind of what he's saying that without having these C phase gates, you're not going to realize MBL. It's hard to read it.
Realize an MBL paramagnet, not an MBL time crystal. The time crystal is where you have the almost time.
Right, yeah. This flipping, essentially, you see this, you get the cancellation. I meant to say these 2 disorders, yeah. Okay. So, but let me show you some basic properties of what this gate sequence is doing. For a second, forget about the entangling gates, forget about the disorder landscape, and you just do pi rotations. That's to begin with, right? You have 20 qubits, they're non-interacting, all of them acting individually, and you rotate them by magnitude of G, and you see that it rotates back and forth, is nothing surprising. You know, they're just doing pi flips. But when you get G away from 1, they do imperfect. They go from North Pole almost to South Pole, and every time they're missing by 3% or so. And you know, that's this pattern of qubits. I'm showing the average behavior. Individual of them would have done the same thing. So there's nothing that profound about these 20 qubits going block sphere rotations. And you go more away from perfect flips, and you know, you see these 2 frequencies in the system. Nothing interesting that profound. But something a little more interesting happened when you turn on the interaction between the qubits, and then you see some phase locking between the qubits. When you go away from these perfect rotations, still you can see one single peak in the frequency, meaning that all of them now are responding in unison, and they are doing the same thing together. So they are getting phase locked to each other. And this was very nice observation that was happened in the first generation of the experiment, that they see this phase locking and they study the rigidity of this phase locking is all very interesting. But it's not that, again, unheard of. You know, you have a bunch of people clapping at the end of a concert, they figure out how to synchronize with each other. So it's nothing quantum about this aspect either. It's very known physics that, you know, systems can phase lock to each other, particularly driven systems. And this has been the physics that has extensively discussed in these former publications. They have a imperfect drive, and then they turn on some disorder. So every qubit, every ion is doing its own frequency of oscillation. And then when they turn on the coupling, they just link to each other. But I think by now it's very clear this is the whole physics of MBL, and we have to really pay close attention to MBL. So from the original definition, we break it down, the definition that I wrote. I'm now writing a more extensive definition that is we translate into a couple of criteria that we have to establish to prove there is a phase of matter and there is a phase transition. And the manuscript and the rest of the talk is about going these criteria to hopefully providing convincing evidence that we did something in here. So we have to show this is a stable phase, it's not a fine-tune, you change your parameters. I show some evidence of that. Still you get this physics going. We have to distinguish between intrinsic dynamic and decoherence laws. Remember, part of the definition was indefinite oscillation. So how are you going to show that? Or we at least did our best attempt in that direction. And as all you know, many-body localized phase and eigenstate order phase. So we have to show all initial states, all configuration of initial states are showing the same physics. And you know, there's exponentially many number of them, so how would you go for that? And then, you know, as every theorist loves to take the system limit to infinity, so we cannot afford to do that. So how are we going to show what's the behavior of the system when you make it larger and larger? And the rest of the talk is providing evidence in these 4 directions. Let me show you that this behavior didn't come for free. You know, you really tune your parameters away from these values that were showing period doubling, you actually lose it. You change this G value far away from perfect 1, and essentially, no matter which initial states you try, you don't see the oscillation. So at least there is some hints that there, as we change this control parameter, probably there is a phase transition that from this behavior is very suggestive. We didn't prove anything in here. We, of course, borrowed numerical to gain confidence in this case. But it shows that, you know, for certain value of G close to 1, you seems to all of the initial states, no matter what initial state, no matter what disorder you choose, you see a period doubling, nicely oscillation. But away from it, it seems that you just don't see it. So at least there's a range of parameters that it works, and there's a range that it just fails to work. Most importantly, we want to show, provide evidence that this oscillation goes forever. Okay, we don't have time to wait forever, so how we do it? This came from figuring out a trick that we showed in an earlier manuscript, how to cancel the effect of decoherence and noise. You apply your gate sequence for some time, and then you apply the inverse of that. And you apply U and then U dagger. And U dagger has to give you identity. But in reality, they don't, and they give you this black line. And this is as we use that to normalize the data and remove the effect of decoherence to the environment. So essentially, the data is when you divide, you can divide this blue raw data by the normalization, and then you get the best evidence that we have that this oscillation goes forever. And here is the average value. Top there is the time resolved version, qubit resolved, space resolved version of it. Now you have 20 qubits that are locked together. They go up and down, follow each other. It's getting a kind of boring pattern, but because they're all doing the same thing. But also you realize away from whatever this phase, we close large G values, let's say, what we call MB DTC phase. Even after you're removing the effect of decoherence, the intrinsic dynamics tells you that there's very good diffusion and there's no essentially persistent oscillation in the system. Okay, let me give you some evidence for many-body localization. So what's many-body localization is about absence of diffusion. So what we do is we consider 2 initial states that are different from each other by just 1 spin fillet. Imagine a chain of 20 qubits, and you say, what happens if my initial state is all 0 versus what is my initial state qubit 11 is up states. And you see the response of the system for when this phase, the phase of the entangling gate is non-uniformly chosen, uniformly chosen from this distribution versus is being fixed at a given number. Of course, depending on your initial state, response of the system, the Z projection, is different. However, when you go few qubits away, it didn't matter what initial state was, and that's exactly what you need for realization for many-body localization. You go away, and there's no effect of it is not sensed. However, when you choose the phi values to be fixed, you see that even if you go few qubits away, still the presence of the memory of the initial state has a very make a clear difference. So being good experimentalists, we cook up a metric to summarize these plots in a single number, the amplitude difference divided by the amplitude summation, and this is what is presented in here. For the case that we claim is in the MBL, you see that you put an excitation and there is no difference, there is no diffusion. And in the absence of MBL, there is a clear diffusion, and that is our evidence that indeed the uniform choices of phi is going to take you away from anybody localization. And here is a cross section of these values of whatever 33 cycle or something. And again, providing more evidence that it seems the eigenstates with G equals to 1, regardless of the choice of initial state and so forth, are all showing the same thing and are showing the localization. So this picture is essentially getting more established. What else? Yeah, so I'm just going to provide more evidence for the fact that there is an eigenstate ordering. So we are going to try different initial states, and we try to show that regardless of what initial state we choose, we see the same behavior. And we contrast it for the cases that, again, the entangling gate angle is fixed. We choose 3 initial states, nil being up, down, up, down, up, down, polarized being all up or all down, random meaning a mixture of up and downs. And you see that regardless of the choice of initial state, we get the same response. All of them are doing the same thing. And in this case, when we are at phi equals to minus 0.4, we see difference depending on the different initial state. And we repeat this experiment for 500 or 400 or 500 initial states, and we see that in one case, they pile up with a very small sigma to mu over the average value. They all pile up around in here, and these cases, these initial states that comes to everyone's mind, these are first choices, these are also show the typical behavior of the distribution. However, when you're away from the localized case, depending on your initial state, you have a very wide distribution, and also these things also are really by no means show the typical behavior of the response of the system. Okay, this was 500 initial states, but this is only a fraction of a % of the size of the Hilbert space we are dealing with. So inspired by our guru and role model, which asked us to do things properly, now we have to check the entire spectrum. So how will you go to check the entire spectrum? The way to go for it is that you make a typical state. We show you the typical behavior of the spectrum. Make one state that shows the typical behavior of the spectrum. So how would you do that? The circuit gets slightly more involved. Let me walk you through that. First, we want to measure 2-point correlation on a randomized state, on a state which is not a product state anymore. I have to make a confession that everything we show in here, I keep showing 2-point correlation function in time, but of course it was a product state. So this ZT comes, Z at instance 0 comes out of the expectation value and just get multiplied later on. There was no actual genuine 2-point correlation measurement here. However, now we are walking away from product states and we have to do proper 2-point correlation function, and the initial state is not a random state, is not a product state anymore. Well, that's where the ancilla comes in. That if you use an entangling gate and couple your first qubit to an ancilla, the measurement of X is exactly giving you what you want. It's a simple math, you can work it out. So that is this initial addition in the beginning of the circuit. And then we want a state to be Haar random in the Hilbert space. We don't need random product state. We need states that are randomly chosen from the Hilbert space. So the way to do it is to introduce a scrambling circuit. You start from a product state, and then you scramble it, and this is similar to the quantum supremacy experiment. You have a layer of microwave followed by entangling gate, and that takes your product state fully scrambled in the Hilbert space of the system. So, and then depending on the number of cycles in this, you have better scrambling or worse. And so after you did that, you're resting on this assumption of typicality, that this pure step randomly chosen from the Hilbert space showing the typical behavior of the spectrum. So with one state fully randomized in the Hilbert space, we are going to predict the behavior of the spectrum, of the entire spectrum. And this is the data, raw data, qubit 11 at G value is 0.94, and the normalization, and we use that to do the proper normalization, removing the decoherence, and you can see we are restoring the essentially what we claim as the infinite oscillation signature. And now this is for a fully randomized state, fully scrambled state. And we continued it for maybe, again, few hundred initial states, and we go for different scrambling depths of circuits. You don't scramble it anything. You have bit strings, you have product state, they are random initial states, random product state, but they're not Haar random in the Hilbert space, and that is this case. And then you scramble it further and further, 2 cycles, K being 2 in here, or 20, and you can see that as you go further and further, you have a better, narrower distribution showing the typical behavior of the spectrum. Okay, so this is our evidence that really what the physics we are seeing is coming from the entire spectrum. I might even finish on time. Okay, this is the last piece of evidence. Is about going to infinite system size. Well, we cannot go to infinite system size. It takes infinite money. What we could do, we can go to a smaller system sizes, in fact. And we can change our control parameter and look at our order parameter and see how it scales with the system size, very standard finite size scaling argument. The order parameter we chose is Edward Anderson order parameter, and for the experts, I can add that we remove the effect of H qubits. There's an H qubit which could give you really strange signals, so you have to remove that. Detail of that in the manuscript. But what the typical behavior is that we go from 8 to 20 qubits, and there is a clear crossing in here, and also below the crossing, when you go larger and larger, the Edward Anderson order parameter get weaker and weaker. When you're above the transition, when you go larger and larger, the spin glass order parameter gets larger and larger. So therefore, we are going to extrapolate and argue that that's the behavior when you go to make a system larger and larger. Okay, I'm good. Okay, but there's one thing, maybe I say a little philosophy to end it. So there was news and people talking about it, and they get all wrong. That's okay. It's very expected. But there's one thing I want to make it clear about realization. Did we realize the phase or not? I think these news say that we realize it. They're wrong. We didn't realize it for this reason I'm about to tell you. We didn't realize it because this system is not closed, it's open. We didn't wait indefinitely to see it. But it's not also that we simulate it. You see, sometimes you come and say, what can you simulate? What's the native Hamiltonian of the system? Our native Hamiltonian of the system is Bose-Hubbard and is open, and you wait, you get 0, 0, 0. It's not interesting to study that. And usually what we do is quantum simulation and try to map the physics. But in this case, this is not just simulation. This is a system, putting aside this openness discussion, that actually you can realize this phase, meaning that is as good as any other system. You know, you can couple pendulum and see if they're going to oscillate forever, or you can couple qubits and see if they oscillate forever. So is in the direction of realizing the phase, but except, you know, the shortcomings that I discussed. but is not also quantum simulation. So there is this very clear distinction, at least in my mind, that I want to say. Anyways, that's all I have to say. Maybe there's one more. Okay, yeah. What did we learn from this paper? I think the value of the paper, at least to me as an experimentalist, is that we are highlighting how with NISQ devices study phases of matter. We're going to be with these NISQ devices for many years to come. So we have to figure out they are not infinite time, they're not infinite in space, and we have to develop techniques to study what fascinates condensed matter physicists on the phases of matter and whatnot. And I think the paper, the point of the paper, strength point of the paper was to tell and discuss how to do these things very carefully and introducing techniques to do that. And I think that's the take-home message of the paper. Thank you.
Thanks for the nice talk and thanks for finishing on time. We have plenty of time for questions.
Can I ask one more? First of all, experiment is really fascinating. If I'm saying something, it's just about maybe a philosophy of the thing. One thing,
you're in good company.
Yeah, I just want to say, so alternative to MBL would be sort of like a glass. And it's sort of much harder to test experimentally. Like, for example, you can do experiment on this glass and you will see it doesn't move. And then you can say it lasts forever. So like, for example, I kind of believe that if you put disorder just on one side of in one qubit, if it's strong enough, you will see exactly the same behavior, even though like no one doubts it will thermalize. And the second short comment about finite time thing, I think it's not sufficient for you to extrapolate it in this way, because of course, if you have finite time, at some point, system size will stop matter. So the fact that you see crossing point doesn't really tell you that you have a phase which lasts forever. So what you have to do really is to do what you did for finite time, then double the time, repeat the whole thing, get a new crossing point. And if this new crossing point doesn't flow at all, which is again very hard to say because it might move a little bit, then you can make a claim. But if you do finite time scaling, of course, you will always get crossing point. So this really doesn't tell you anything about extrapolation. Yeah, at finite time, you will always get crossing. Because at finite time, at some point, you just stop feeling your system size.
You don't believe that?
No, I'm just saying that this you expect no matter whether you have MBL or you don't have MBL, because this is what I'm trying to say.
But
if,
this
you
is
have
about...
if you waited for 100 seconds, after you reach system size, say 100, you don't feel system size anymore. So you will feel that, yes, you go somewhere.
Yeah, sure.
Yeah, so
No, you got to go here.
Yeah, I agree with you that, you know, in any experiment that we have access to right now, we're limited by finite size and time, and the types of questions you're raising on MBL and, you know, whether we can probe it in some asymptotic limit of infinite sizes and times, we're not going to be able to resolve that by experiment. So that's a completely fair point. The goal of this is, if you believe that there is some very, you know, I think I believe that there is MBL, you say that there's some very long-lived pre-asymptotic regime, that's fine. This can at least distinguish between very long-lived pre-asymptotic regime and things that decay very fast. So a lot of the other experiments, they probed one state. If you probe like a random state, it'll decay super fast. If you put disorder on only one site, yes, your level statistics won't be able to tell the difference, but an autocorrelation measured at every site will. So there are various things you can do to distinguish between just decays fast and very long-lived, slow pre-thermal regime. If that's what you want to call it, I'll call it MBL, and we at least address that.
Yeah, I definitely agree with this. We know one classical example, Fermi-Past-Ulam problem.
Sure.
And it behaves in some way exactly in the same way. There are no oscillations, so it's not time crystal, but in a way it's very similar. So it either thermalizes immediately, or it takes you like, I don't know, ages to thermalize.
That's right.
And
I just don't think
figure out, yeah, it's probably not forever, but it takes like very long time.
Yeah, and I just don't think we have the experimental or numerical techniques to be able to distinguish that. I will say one thing here that, people often say that pre-thermal time crystals, again, you can't tell the difference between forever and what we have access to, but there's a very strong initial state dependence. It's like if you look in this vanishing part of the spectrum, which is polarized states, then it lasts a long time, seemingly forever. But if you look everywhere else, like literally the entire other spectrum, it decays rapidly. So that you can distinguish experimentally. So, okay.
Oh, okay. I just wasn't talking enough. So I want to understand actually on this plot an experimental point, which is you're doing finite time averaging at 50 cycles or something like that. And so, for example, on the nominally non-glassy side, it's actually saturating as a function of system size. How long are you able to study decay of this spin glass order parameter in these actual systems? Like if I continued that plot at later times, how far can you go? Can you actually explore something about how this decays in the non-glassy?
In time, right? We chose
to later times, like.
I think we are by now we have gone. By now we can go maybe 150 cycles or so, and then after that, because you have to divide two numbers which are getting to zero, you have to average much longer time to get the good signal to noise ratio. So we just lost patient. Other than that, up to 200 or so that we have gone is the same. But
the belief is that somehow after this normalization, which is a little bit uncontrolled, nevertheless looks time crystalline, at least on the time.
The rest we attribute to intrinsic dynamic, right. After the division. So for this case, we just chose between 50 and 60 cycles. I guess you could go deeper, but then you had to average longer.
Okay, thanks.
Questions?
So, can you go to a previous slide? The one where... So what is that beating there? So this is the signal of the whole spectrum in a certain sense. You're scrambling and then you're entangling just one qubit and then you're applying the time crystal sequence, right? So what like this is referred to a certain state or to a certain product state or after the scrambling? This
is an instance. You choose a bit string, random bit string.
Okay.
You scramble it, I forgot, let's say maybe K for 10 cycles, 10 scrambling cycles. And then you measure 2-point correlation function, but there is a minor caveat that you have to read it through an auxiliary qubit.
So it's the signal of the ancillary qubit.
This is, I'm saying that what we are interested is the 2-point correlation function, but since this is not a product state anymore, you have to do a little assistance.
Okay, but okay, and why do you have that beating?
This beating?
Yeah.
This is coming from L bits of MBL. Is not right. They interfere initially and they cancel out, but these are the L bits of the MBL.
Okay.
This is only one realization. This is not disorder average.
It's not disorder average, so you have the
okay.
There's a question from the online audience, Joshua.
Hey, Mohammed. Hey, everyone. So I just want to ask a question regarding this. So you do this UF times UF dagger, and then you see this exponential decay envelope, and that fits with this oscillation envelope almost exactly. Does that actually mean your sort of decoherence has a simple models so that you can do this exactly? I would expect this is a pretty complicated,
Yeah, I think when
it's not here. Can you hear me now?
We can hear you, Joshua. We heard the question.
Oh, can you hear me now?
Yes.
Okay, good. Sorry. Yeah, let me repeat my question. So basically,
we heard the question.
Sorry. Can you hear me now?
Yes, we heard you and we heard the question. Pedram can answer.
Okay, good.
Pedram, can you?
Yes. So Yeah, I think in the limit of full, when you're the depolarizing channel model is very good in this case. Yeah, so at the end of the whole thing, there's a strong scrambling in the circuit. So this is a very, very good model. There's no, yeah, all your coherent errors get averaged out, and you're only left with decoherence that you can take out easily. Yeah, at the end, it's very simple.
So you can just model this as a driven dissipative system. You have some, depolarization and
exactly. Yeah.
Okay, good,
roughly speaking, yes, that's correct.
Okay. Thanks.
So actually, maybe if I can ask a question. So this is just dephasing, and this is just basically single side dephasing, and that's all there is to it?
No, also control error would be getting scrambled and appear there. So it's a mixture of systematic control errors and dephasing. And photon loss, energy losses, all of the same time.
A few more minutes if there are more questions. There's one more question that's coming.
So this is really just a big picture question, but now we have, a handful of experiments that have realized time crystals or whatever you want to call them, up to these caveats in one way or another. So what are you going to do now? Should we be looking at excitations of these things, or are there different time crystal and phases to explore? What do we do?
What should we do next? Yeah, but I think Vedika was very clear on this, but there was something they do to agree. I think that was very momentous. That, we're not going to resolve this infinite time. So if that's the next question you're going to ask us, you're not going to get better than this. So we have to get clever with our questions or our subject of study. I don't know what else I can add to time crystal studies.
Thank you very much for the very engaging talk. Let's thank Pedram again.